Welcome back, ladies and gentlemen. Today we're going to talk about how to find the area between two curves. This should be a fairly straightforward concept so long as you remember how we constructed the idea of an integral in the first place. As a reminder of how we did so, I'm going to show you a few graphics from when we did that. We wanted the area under a curve, and we eventually did some work to get the dx and the f of x, but the way we started was with a simple Riemann sum, which looked like a whole bunch of rectangles being added together. And what we did was we aligned them so either the left-hand corner or the right-hand corner or sometimes the midpoint or even trapezoids were lined up with the function value, and we added them all together. We used summation notation to help us express that without having a whole bunch of addition signs. And what we did for the integral is we just started making more and more rectangles. So we took n as it approaches infinity, and we used an integral notation to represent that area. So now we have an infinite number of infinitely thin rectangles being added together to form the area. Now, if we examine each one of those rectangles, this is one kind of blown up in the Riemann sum sort of way, the biggest take home that we needed from that unit was for you to recognize that the height of each rectangle was dictated in some manner by the height of the function itself. So the distance from the x-axis to the top of the rectangle is the y-coordinate of the function. And that was true whether that was a left endpoint, a midpoint, or a right endpoint for the rectangle. One of those y values defined the height of the rectangle. That remained true as we took the limit as it approached infinity and used integral notation. So in essence, these little infinitely narrow rectangles being added together are still being dictated by the height of the function. So if we change the problem a little bit, and instead of going from the x-axis to a function, like from the x-axis to the function, and instead we go from curve to curve, well, then we have to think about how this would be constructed in order to find basically another rectangle. So if we take a closer look at just that one example, it looks like if we insert a rectangle instead of immediately jumping to integral notation, well, then we need to find the height of this rectangle, and it is defined with a left-hand endpoint anyways between f of x up on the top and g of x on the bottom. So how do we get that value? Well, let's put some numbers to it. Let's say this has a height of y-coordinate of 5, this has a y-coordinate of 3. To get the height of this rectangle, we would take 5 minus 3. So we would be taking the y value from f and subtracting the y value from g of x, or just basically subtracting the value of g of x from that of f of x at each and every x value to form our integral. So when we want to find this distance, we can, just as a second visualization here, we can take the total distance from the x-axis up to the top curve, and we can subtract the distance from the x-axis to the bottom curve. And if we take blue line minus red line, we get the green line. So we get that leftover distance. And that's how we do it. We take top curve minus bottom curve within our integral, and that will give us the area through that smooth curve there. So I think the best way to explore this topic a little further is actually to go right in with a fairly complicated problem. This one, for instance, basically requires the use of a calculator. It's very difficult without. And it's designed in such a way to give you as little information as possible. So if our goal is to, we have two goals. We have one that says write no more than two integrals to describe the area between the two curves as shown. So we want to describe this area with an integral and this area with an integral, or possibly both with one. And the second thing is we actually want to go ahead and find this area. And it says find the total area, so that's just kind of telling you that it wants you to find, consider this being positive and consider this being positive areas. So what we're going to do is we're going to take top curve minus bottom curve. So in this case, if we take a look at the top curve, that is h of x. So we're starting to build rectangles inside here. So we're going from top curve h of x minus j of x to find the height of that rectangle. But then you'll notice that at this intersection, the roles switch. So if we'd started writing an integral from this spot, top curve minus bottom curve is now from j of x to h of x. So we just have to swap which function is being subtracted from which. And then the additional difficulty is that we don't know exactly where these points are. But if we wanted to generalize it, just so we can kind of get a grasp on the problem, let's name these intersection points A, B, and C. We'll have to go find those, but we can write an integral. The first one describing this area with h on top, so h minus j, and the second one with j on top, so j minus h. That would look like this. Now, we can go ahead and start finding our intersections and plugging in our functions, but before we do so, I want you to consider one more thing, which is, let's say we ran an integral from A to C with h on top the whole way. So taking the value of h and subtracting the value of j. So right here, h is bigger than j. So if I take h minus j, I get a positive number. But if I go past the intersection point of B, then h of x is a smaller number than j of x. So, if this has a height of 1 and this has a height of 2, if I take 1 subtract 2, I get a negative number. So as I go along and I start and accumulate area all the way up until B, I'm accumulating positive area, but then this area would be counted negative if I didn't switch j of x to be on top again like this. So if I just ran a single integral from A to C with h of x on top, this would be counted as negative. Now we can actually get around, this is the correct area, it would just be negative. So we can get around that and condense our integrals into one integral by considering the absolute value of this. So if I throw an absolute value around the difference between the functions, and I could do either order, j minus h or h minus j, it will count this area as being positive. So I can do one integral instead of two, which is awful handy when you're, pressed for time doing an FRQ with a calculator and a whole bunch of numbers flying in your face. This ultimately reduces the number of steps that you have to take, and it makes your life a little easier. So to do this, we have our function definitions, so we can type that into y1 and y2. And we can go ahead and go find these intersections. I need intersection A and intersection C for this integral, or if I wanted to do it as two separate ones, I would also need B. Remember that your calculator has the ability just to find intersections on a curve, and you do that. I'm on the first curve, I'm on the second curve, and then I'm going to guess where that intersection is, and your calculator will store that intersection value under X. Now again, remember when you're doing an FRQ, you need 3 digits of precision. So it's really a good trick to get in the habit of is storing this value under a dummy variable just so you can reference it later with its full precision there. So remember this trick that your calculator will store the value under X, and then you can store it under something that is not overwritten every time you calculate an intersection, and then you can use it later. So I went ahead and did that for all 3 of these points. And from there, I just had to type in this command. So this is the integrate function from the math menu. And you'll see that I inserted an absolute value. So I'm going for the simpler single integral situation. So here's my absolute value bar, which you can find under the math menu and the number tab. And then we are going to integrate the difference between y1 and y2. And you could have those in either order because we have the absolute value. If you don't have the absolute value, it does matter. But since we have the absolute value, all we're doing is finding the difference between the two and always counting it as positive. We want to integrate with respect to x from the intersection A to the intersection of C. All that in one line gets you a final answer of 5.964. And you're done. One line in the calculator just with a little bit of setup and a little bit of thinking. Now, it's also common to have to do these problems without a calculator. So here's a classic. Find the area between sine and cosine in that shaded region right there. So the first thing you have to do is you have to kind of identify where your intersections are, and without a calculator you can't do that little intersection key, but you know that this intersection is where sine is equal to cosine. So algebraically you set the equations equal to each other, and then you have to think about your unit circle about where is the sine value of an angle equal to the cosine value of an angle. And that happens at pi over 4 and 5 pi over 4, as you can kind of see in these pictures. And then the next biggest thing is you have to figure out which function is on top. So because we have to take top minus bottom, we don't have a fancy built-in absolute value bar when we're doing algebra like this. So we're going to take this curve, which if I trace it back down, it goes through the origin. So this must be my sine curve. So I'm going to go sine minus cosine, and I'm going to run it from pi over 4 to 5 pi over 4. So there's my integral. Do an antiderivative. So we're going to have a negative cosine. That negative will be maintained. And then we're going to evaluate this at 5 pi over 4 and pi over 4. And man, are there a lot of negatives in this one, just to give you a little heads up. Look at all of them. So the cosine and sine values should be the same. We kind of figured that out when we set them equal to each other. We have a subtraction symbol because we're evaluating 5 pi over 4 and pi over 4. And then, of course, these each have a negative sign built in. If you do all that correctly, you'll get 2 times the square root of 2. So the moral of this story, pay very close attention to negative signs because it makes a huge difference with just one of those out of place. Our next example is finding the area between two curves where they switch, and this is going to be another one without a calculator. So we have to find these intersection points algebraically as opposed to graphically using a graphing calculator. Now it looks pretty obvious that they're at -2, 0, and 2, but we can't assume that, so we have to confirm it. So we have to set the two functions equal to each other, combine like terms, and then it is possible to factor out a 3x and then factor out the remaining x squared minus 16 into x squared minus 4 into x minus 2 and x plus 2, giving you solutions of -2, 0, and 2. So those are going to be our boundaries, just like it looks. And then we just have to figure out which curve is on top because we can't do the absolute value. We have to manage it ourselves. So we are going to say this curve is on top. If I trace that over here, that is our f of x, and our g of x will be on top for the second integral. So I'm going to go from -2 to 0 with f of x on top, and then I'm going to go from 0 to 2 with g of x on top. And that integral will look like that. Evaluating it, not too bad. Just combine like terms as you subtract them. Remember to distribute the negatives, of course. If you do so, the like terms will combine like that. Then you anti-differentiate. So we're going to get 3/4 to the fourths with an x on there, of course. And we're going to evaluate that at -2 and 0. And this one you're going to evaluate 0 and 2. Basically, the only difference is a sign change because we just changed the order of subtraction ultimately. And if you do all that correctly with the correct negatives in the correct places, you'll get a final answer of 24. Thank you for your attention. I'll see you next time.